Hello everyone, it's a pleasure to be here. Today I will talk about my work on the symbiosis of program analysis and biologically inspired computational models. At the end of this talk, you'll gain an understanding on how we can apply traditional computer science principles into chemical domain. That is, how can we program with molecules such as DNA. Also, you'll learn about connections between different models of computation through examples of connections between neural networks and chemical reaction networks. Let's dive in. I fell in love with programming since I was first introduced to it in my high school, and I was particularly excited by the fact that we can teach, that is, instruct machines to solve complex tasks for us that would even us humans take a long time or even be infeasible to do by hand. I started by writing in traditional imperative program languages which target CPU architectures. And I was intrigued to find out many years later that programming is a much broader term than we usually think. For example, we can program neural networks with data. Now, we actually remove the need for explicitly specifying instructions, but instead we can just provide the data and program will be inferred automatically. So this opened a path to previously undoable applications in computer vision, natural language processing, and many other areas. The least explored, yet quite fascinating to me, is programming of chemistry, that is, of biochemical systems, which also has a potential to transform many areas, opening a path to novel applications. So while I quite enjoyed programming, what I found a bit less fun is presence of bugs. And bugs are inherently present in all three models of programming. And goal of my research is to make programming easy, efficient, and error-free. Easy meaning to make it intuitive and natural for a user to describe desired intent. Efficient meaning that programs written at that level translate to efficient low-level implementation. And error-free naturally means that programs written do not have errors. Now, areas of software engineering, molecular programming, and machine learning are tightly connected to the programming, to the domains I mentioned on the last slide. So in my research, I explore connections between these different areas and models of computation, and in this talk I'll particularly focus on molecular programming, that is how we utilize software engineering and machine learning to help the field of programming with chemistry. I'll start by talking about CRN++, which is the first imperative molecular programming language that we designed. Then I'll continue with a technique that explores space of chemistry and finds the basic modules, so what chemistry naturally computes. Then I'll talk about the connections of neural networks and chemical reactions. And this would wrap up the main part of the talk. Then I'll just briefly mention my work at the interconnection of machine learning and software engineering. So you might wonder, why would we even care about programming with chemistry? And one fundamental reason is that we cannot embed electronic logic into living and synthetic biochemical systems because it's not compatible with those environments, while on the other side, chemical logic is naturally suitable and compatible with those. So why would you want to embed logic? Well, there are many applications that could be enabled by doing so. One, we can help increase the yield within bioreactors by designing chemical controllers that can smartly interact inside. Two, we can help in manufacturing complex nanostructures and materials, where we can basically construct small structures or molecules that, based on local interaction rules, they can interact with each other and assemble a larger pre-planned shape. So this shape is on a tiny, minuscule scale, and we can construct complex shapes on such a tiny scale only using methods like this. We currently don't know how to do it with other techniques. And 3, we can design smart drugs for health, where we can imagine having chemical controllers that can sense a type of a cell, for example, a cancer cell, and release a payload neutralizing that cell when it's detected. This is to mention only a few of potential applications. Now, I imagine that in designing chemical computation, we will have different layers of abstraction similar to what's currently found in electronics. At the top, we'll have a high-level programming paradigm that makes it intuitive for a user to specify desired intent. Then we need a compiler from that level to a level of chemical reactions. So note that behaviors are in chemistry are naturally describable by chemical reactions, and thus this is a natural middle layer. So I see that that the top level is akin to programming languages we have, such as Java, but this level of chemical reaction is akin to assembly layer in electronics. Then we need compilers from chemical reactions to chemical hardware. So chemical reactions can be abstract, just describing behavior, but now we need to implement it with physical molecules such as DNA. And DNA has so far been used the most because our level of understanding of it and ease of use. Now there are open questions at all parts of this diagram. For example, at the top, the question of what is the right paradigm to program. Should it be an imperative, concurrent, or should it possibly be neural networks? Then, how can we efficiently compile from these programs to a level of chemical reactions, where even our understanding of what efficient means is not fully developed? Then on the level of chemical reactions, we are still in search of basic modules, that is, the modules that efficiently compute certain functions and should be used as building blocks in supporting our high-level programs, basic instructions. Then we need tools for systematic translation from chemical reactions to hardware, where currently we need to do a lot of manual work, and that needs to be automated. On the level of hardware, there's a question of biointerfaces. The hardware we build, how do we make it interface with the natural environments? Also, question of different sources of error, where when we build, let's say, realize a chemical reaction with DNA, there's some sources of error we don't fully understand. We cannot fully predict what will happen in wet lab. And finally, question of scaling up, that is, scaling up the size of the hardware that we can build and scaling down the cost. Next, I'll talk about my contributions that tackle some of these questions. But first, let me give you an intuition on what it means to compute in chemistry. So we'll take a look at the reaction A plus B goes to C. Indeed, the default language to describe chemical computation are chemical reaction networks, that is, sets of reactions. And now to describe A plus B goes to C, let's say we have a molecule of A as shown, molecule of B as shown, and they are compatible with each other, so they can interact, producing molecule C. You might wonder, what does this CRN compute? Well, the reaction can happen as long as both A and B are present, and when one that was initially present in lower quantities runs out, then production of C stops. So thus, amount of C, molecules of C produced, will be equal to the minimum of A and B initially present. You can also describe behavior of CRNs with a set of differential equations, where this is a set of equations for the above CRN. And now what you can do is you can numerically solve it and simulate to see how it changes over time. So we see concentrations of different molecules over time, where we here initialize values of A and B to 3 and 2 respectively. Now, since we talk about programming, we somehow need to define inputs and outputs of our programs. So input to our program are initial concentrations of A and B. What is the output? Well, output is the final concentration, final value of C per our convention. Another thing that I want to note that CRNs are highly complex. Here is a simple two-reaction CRN. One thing to note is also that CRNs are inherently parallel, meaning that every reaction occurs in parallel with any other reaction. This is a set of equations that describe the above CRN. Now we can actually simulate to see how molecules change over time, and this is the behavior we get. One thing that I want you to note, that for the simple two-reaction CRN, we have this highly complex and nonlinear behavior. Thus, it's very hard to encode the desired intent in a set of CRNs because everything happens in parallel and it's nonlinear, so it's hard to actually think on this level of reactions. My goal of my research is to make programming abstractions that make it more intuitive to describe desired intent and that then translate to the level of chemical reactions automatically. Let's restate that goal. So we want to enable a user to write in a high-level language such as C or Java and then build a compiler from that language down to chemical reactions, which then can be simulated or eventually implemented in a lab. So let's see how we can build such a language. I would argue that one of the crucial things in building a language is a choice of a basic primitives instructions that should be used as a building blocks to support language. And here I'll show you what primitives we chose. One such a primitive is a load CRN, basically loads value of A into B. If you want to let's take a look at the plot. So here is value of A, and no matter what the initial value of B is, B will converge to the value of A. Then we have add CRN. So what it does, we have inputs that are A and B, while C approaches the value of A plus B. So C is the output. And now we can write this add ABC instead of writing the CRN in our language. We have also others, such as subtract, multiply, divide, square root, and so on. Now, these modules were not chosen by chance. One important property that they have is property of composability. What that means, if we stack up a different CRNs, such as multiply and add, we get the behavior. So basically, this multiply does x times y and stores into k, and addition says k plus z goes into w. Effectively, what you would expect is x times y plus z by stacking up this multiply and add. And indeed, if you change this with the CRNs, with these CRNs we designed, you have this composited behavior. But that doesn't have to be case in general. You can have two CRNs, but composition of those two CRNs doesn't have to be a composition of the functions that they individually compute. Okay, so that's one important property. So we now have the primitives, but we need other constructs to support our language. And due to the time, I'll just illustrate our language on an example. This is the algorithm that I'll use for illustration purposes. It's GCD, or greatest common divisor, computing GCD of two numbers. So what it does, these are inputs A and B, and while they are different, a smaller value is subtracted from a larger value. And this is stopped when A and B become equal, when they are actually equal to their GCD. In CRM++ that we designed, this is how the program, equivalent program would look like. So we would load A and B into temporary variables. You don't have to know, I won't go into details why these temporary variables are needed. But then you compare A and B, and then in the next step you can do conditional execution. One thing is, this step constructs separate execution in time, but I mentioned before that everything happens in parallel, so how is this even possible? It shouldn't be. Okay, so to implement that, we rely on a construct called chemical oscillator. So what it does, it has a different chemical species which concentrations oscillate in time, in such a way that when one species is at its high value, the others are close to zero. You can use these species to catalyze different reactions and in that way achieve ordering. Okay, so what we can now do, we have a compiler from CRM++ to chemical reactions which we can then numerically solve and simulate. And let's do that, initialize inputs to 32 and 12 and see how CRN behaves. This is the behavior. So we start with the A equal to 32, B equal to 12, and now since B is smaller than A, B is subtracted from A, and we get A to be 20, B 12, and this process is repeated until they both become equal to 4, which is equal to GCD. The changes happen on certain phases of the oscillator, and this is a continuous curve, just to stress here. Okay, so what did we achieve with CRN++? So we designed a high-level programming paradigm that makes it easier to encode desired computation. It's the first imperative molecular programming language as far as we know. It exemplifies a rich set of behaviors that chemistry can perform. You can write very complex programs and see that chemistry can do it. But there is one open question, and that is the feasibility of implementation with chemical hardware such as DNA. And indeed, programs that translating CRN++ programs to CRNs produces very complex CRNs that are not immediately feasible for implementation. And I'll next talk about how we tackle this issue. So what we did so far is we had a vision of a high-level language such as C or Java. Then we came up with the primitives or basic building blocks that should be basic modules to support such a language. But where do these modules or primitives come from? And even more, are we possibly shoehorning ill-fitting electronic paradigm principles into chemical domain? Because we mainly took inspiration for the modules from electronics. And next I'll talk about a technique that can answer this question and help us find modules that chemistry naturally computes. So what we did is we used Alloy, which is a declarative language for specifying behavioral and structural properties of systems developed at MIT, and we model CRNs using it. First, we have signals for species and reaction. The reaction consists of reactants and products, which are sequences of species. And then we add certain facts. These facts actually constrain the system. At least one reactant means that all reactions have a non-empty set of reactants, which we expect. Then we add some other facts that is constraints. Given the model of CRN we wrote, we can now, Alloy allows us to translate this to Boolean logic. And then from Boolean logic we can input it to a SAT solver, which will give us all instances that satisfy our specification. In that way, we can enumerate all CRNs that satisfy it, which we do. Then we have a next part in our technique, which is called analyzer. So what analyzer does is, given a CRN, it can say which function that CRN compute, such as a plus b equals to c for the minimum, as you already saw. And now we run analyzer for for all other CRNs, and we wonder what can we find. Let's see that. So we found interesting CRNs, such as maximum CRN. It computes maximum of inputs A and B and stores that value into Y. Another interesting property of our technique is that it guarantees minimal networks. So if a network is found to compute a function, then that's a minimal network in terms of number of species and reactions that compute it. We found also ReLU CRN, and ReLU was particularly interesting to us because ReLU, rectified linear unit, is a default activation function used in neural networks. And now you might wonder, how do we represent negative numbers? So for that we use something called ULRel. Note that in chemistry you cannot have negative numbers, as all molecules are quantities or concentrations. So to represent negative value or support negative values, we accept this standard where a logical value of A is represented by a difference of quantities of physical molecules of A plus and A minus. And in that way, so the ReLU computes Y, logical value of Y, is equal to the ReLU of X, where Y is defined by difference of these two molecules and X by difference of these two molecules. Then absolute value, we also discovered absolute value function, as well as min-max CRN. So this CRN computes both maximum and minimum at basically one CRN that has two outputs, maximum and minimum. And it's more compact than having these functions separate. So now let's focus a bit on ReLU. This is how the plot looks like. For x less than 0, it's 0, otherwise it's x. The CRN we found is very compact. It consists of only two reactions. And so this is the analysis why it computes what it computes. So just know that Y is actually equal to the amount of Y plus produced and Y minus produced, which if you do certain calculations come to ReLU of difference of x plus and x minus initially present, which is actually ReLU of x. And now, okay, so what is the contributions of this approach? It's on the layer of chemical reactions, and we developed a technique, a tool for automated exploration and discovery of CRNs. Using it, we discovered compact CRNs, such as ReLU. Also, the CRNs we find are rate independent, where rate independence, I'll stress why it's important later on. Okay, so now, first what we did, we had a vision of a high-level language and we came up with basic modules. Now we've discovered some new modules, very compact, and we wonder, can we utilize them to design even a better programming paradigm? I'll talk about neural networks and chemical computing. On one side, we have a model of neural networks, and on the other side, we have a model of chemical reactions. Is there a connection between these two? And indeed, we found a connection between these two models, and that connection is so tight that the class of neural networks and the class of CRNs can be considered the same thing. This discovery is grounded in our discovery of ReLU CRN using technique shown previously. So what does this connection bring to us? Well, it basically builds a bridge between neural networks on one side and chemical reactions on the other side. So how can we use this bridge? Well, this bridge opens a path to deep molecular programming, where we can use deep learning and train a neural network using deep learning. Now we can utilize the bridge and jump over from a neural network to a chemical reaction network that has equivalent behavior. But how is this bridge, so what does this bridge consist of? Let's see that. And this is part of our ICML and PNAS papers. So the bridge, actually, I'll illustrate on the translation scheme, where this is a model of neural networks. So you can note, okay, this is a neural network. This is how we can decompose a neuron basically into a weighted sum and activation function, where we only use ReLU, which we don't consider to be a big drawback. This is the scheme. So here are the components, different components that the neural network consists of: symbol, equation, what does that mathematically represent, and the CRN implementation of that component. Where for fan out we have this CRN, for a weighted sum we have this CRN, where let's focus, I'll illustrate it, okay, let's focus on this part, contributor to weighted sum. So input xj is multiplied by pj divided by qj, that's a weight, and that's contributed to y. This is implemented with two reactions. So note that we use dual rail convention, so we have to have plus and minus pieces for each number. And now looking at this reaction, so we have qj molecules of xj going to pj molecules of y. In that way we get this rational weight on the left, pj divided by qj. ReLU is implemented with CRN I shown before. And finally, bias terms. Bias terms are simply implemented by initializing certain concentrations of certain species to appropriate values. So one particular class of neural networks we were very interested in is binary weight, where allowed weights are -1, 0, and 1. This kind of networks is popularized in deep learning community, and while we support translation from arbitrary weights, this is very appealing because weighted sum is simplified, and thus it causes only unimolecular and bimolecular reactions, and thus it's more feasible for implementation in chemical hardware. So here I briefly mentioned before rate independence. Let's expand a bit on what rate independence means. So I'll illustrate it on this simple two-reaction CRN that computes function 2/3. We need to define a matrix called stoichiometry matrix. What it does, it says that, so how each reaction affects different molecules. First reaction, specified by first column, decreases amount of x by 2 and increases r and y by 1, which is the case if you take a look at the first reaction. So now let's look at the state space, where a state is defined by quantities of different molecules. Like state A has 10, actually concentration. X is of concentration 10, while R and Y are equal to 0. Now by multiplying stoichiometry matrix by a vector and adding to this state, we can see what states we can end up using this CRN and starting from this state. So we can reach this state C if we multiply M by a vector that specifies how many times each reaction occurs. And then from C we can do the same and reach state B. So this state B is very important because X and R are 0, and because of that no reaction can fire, meaning that we cannot exit state B. This is a stable state. So for non-competitive networks, those are the networks that our neural networks translate to, we prove following. If there is a path from state A to state B, as one shown here, and B is a stable state, then A converges to B for any rate constants on the reactions. No matter at what rates these reactions occur, then state B will be reached. This is the path that mass action kinetics would take. You see that it will also reach state B. So furthermore, we prove that if there is a path from state A to some state A prime, then this A prime also converges to B. What all of this implies is that it makes physical implementation easier, because now when you design molecules, you don't have to worry about rates of individual reactions, and they are very hard to tune. Second thing, it enables easier analysis. You can do this straight line reachability as we shown, and in that way you can prove what the CRN computes. You don't have to worry about ODEs. So let's illustrate our technique on some experiments. So this is MNIST dataset. We train a neural network on it, which on its inputs receives basically pixel values of the image, and on the output predicts what digit is there. Output unit that has the highest value is the digit neural network recognized. Using the bridge, we can translate it to chemical network. We need to initialize it for the same input, so for each pixel value we initialize some chemical species. Now we can numerically solve it, and this is the behavior we get. So these are the outputs of the chemical network. We can see that output y0 is at its highest value, meaning that the chemical network detected 0 as the digit. More importantly, outputs of neural network and chemical network are equivalent to each other. And that's exactly what we wanted. So next we move to datasets that are more closely aligned with intended usage of this technique. So for that, we take a neural network that on its inputs receives gene expression levels and is trained to predict the virus type, virus that's present. This neural network is of course trained in silico, then translated to chemical network to confirm behavior. So this is more closely aligned to intended application because gene expression levels are naturally available within cells. So next, we do spatial pattern formation, which has important applications in synthetic biology since tissue and organ engineering rely on it. To model that problem, we have a neural network which on its inputs receives x1 and x2, representing coordinates, that is position in space. And it's trained to produce color. In this way, you can train a neural network to effectively learn a pattern. Based on the position, it will say what the color is there. We translate this to chemical logic and then show via simulations and proof that the behavior is equivalent to neural network. Now, spatial pattern formation has been explored so far a lot, and so what previous authors did is for French flag pattern that they built a customly designed system. What our approach in principle allows is that for any pattern, such as heart, we can train a neural network on that pattern, and then we can translate it to chemical logic that implements that pattern. Okay, now I'll slightly digress, quick digression. So we were wondering, this is one hypothesis that we wondered about. So we have a neural network and we learn it on a heart pattern, so you can see the confidence of neural network in its outputs. So neural network is of course less confident on the borders of the shape, but it's more confident further from the border. Now for the CRN, we look how long it takes to converge, for chemical signals to converge to their final values. What we know is that convergence time is larger on the borders of the image. And this is the hypothesis where we hypothesize that if neural network is less confident in its output, it will take longer for CRN to converge. We didn't prove it yet. But on a larger scale, a question that arose in our mind, so what you have basically, you have a neural network, and you can provide some inputs to this neural network. Then you can read out the values at different points of this neural network, such as this N1 node has value -2.2 and O1 has a value 1.56. Using our approach, you can translate it to a CRN, and you can simulate behavior of CRN over time, basically concentrations of different chemical signals over time. And there is chemical signal corresponding to these different parts of neural network, such as to N1 neuron, that reaches the same value. There is also chemical signal that corresponds to O1, output unit 1, reaches the same value. And what we've wondered is if we get actually this time domain, and by observing the behavior of this signal over time, can we actually infer something about behavior of neural network that's not so easy to infer by just looking at the neural network on its own. So I ended up with digression. Let's go back to the main part of the talk, main stream of the talk. So what I so far talked about is mostly theoretical, but how can we implement CRNs in hardware? So this reaction A plus B goes to C, you're already very well familiar with, and these are the different DNA strands that represent A, B, and C. Those are single-stranded DNA molecules, where C is captured within this gate, so it's inactive. So what happens is that molecule of A basically interacts and displaces part of C, then molecule of B comes in and displaces other part of C, effectively releasing molecule C. And now A and B are captured, inactive, and C is released, effectively realizing reaction A plus B goes to C. So this is our DNA strand displacement implementation of the ReLU CRN. So we have two reactions modeled with this strand. So X plus and X minus are inputs. They are also single-stranded DNA molecules, where Y plus, Y minus are outputs, also single-stranded molecules. We have this fuel species, and X plus, so this part of X plus is complementary to this plus of the fuel species, so it can come in here and displace this part of the fuel, which is actually Y plus. And it leaves us with this molecule M. M actually can interact with X minus, where this part of X minus is complementary to this part of M, so it can come in here and displace this, which is Y minus, effectively realizing the second reaction of ReLU. Okay, so we performed a wet lab experiment on a spatial pattern formation problem. So this is the pattern we focused on. It's a Longhorn, Texas Longhorn, which is a logo of UT Austin, University of Texas at Austin. This is a discretized version of it that we use to train a neural network on. Neural network we trained has inputs x1, x2 position and produces value y, which denotes if the pixel is orange or white. And okay, what neural network learned, if you discretize when y is 0, then it's orange, otherwise is white, then it's directly equal to this pattern here. But if you look at the real values produced, then this is how the outputs look like. Then we utilize our bridge shown before to translate this to a chemical reaction network equivalent to the neural network that learned pattern. The new part that comes in is our realization, that is design of DNA molecules. So this is how it looks like. We have inputs x1 and x2, single-stranded, representing inputs, and we have outputs y plus and y minus. So note that these outputs have fluorophore and quencher, where fluorophore emits the light and quencher captures the light. So when they are next to each other, you cannot see light. But when they separate, fluorophore and quencher, then you can observe the light. And these two fluorophores are at different frequencies, so they have a different spectrum of light. Now, when you initialize x1 and x2, what will happen, they will go through this system of the neural network, and some strands will displace this output part, which will then start emitting light. And then by observing the light signal, you can see how much of the output has been made. By performing such experiments, these are the results we get. And these results are very close to the ideal, that is to what the neural network learned. And in that sense, we successfully implemented a neural network in DNA. This paper is in preparation. Now I want to stress that DNA has been utilized as a powerful computing substrate by many scientists. So scientists built a DNA robot that performs cargo sorting. Also, an RNA robot that can compute directly inside of cells has been built, as well as a DNA robot that can perform cancer diagnosis in a serum. So So what are the contributions of this part, of the DMP, of the bridge between CRNs and neural networks? It's twofold. On the level of high-level programming paradigm, so what we enabled is a powerful method to program CRNs, now with data deep learning instead of imperative programs. On the other side, we also perform wet lab implementation, and our approach is very feasible for implementation. We also explore this rate independence, which we believe is very important which contributes to implementability. Because now you don't have to worry about the rates of individual reactions, which make it easier to assemble molecules that implement what we want. And the system is more robust to error. To put this all research in a broader picture, let's briefly talk about analog computation. And here is one ODE system or a CRN that computes bubble sort algorithm. Note that CRNs are also analog type of computation. So this bubble sort is a simple algorithm, but it took us a long time to understand how it actually works in this analog world, which implies that we currently don't know much in how we encode computation in analog world. And I believe by exploring analog computation in general, not only we will get a better understanding on how to compute with chemistry, that is CRNs, but will also enable other applications. For example, there are startups that are currently building analog computers that run neural networks. And the advantage of analog computation is that it requires less components to build, and it has much more power efficient computing. Okay, so I wrap up my part of talk about molecular programming. Now I just want to mention that I also worked on this connection of machine learning and software engineering, where I built a technique machine learning technique, neural network that can detect the type of bugs called variable misuse, where a variable is incorrectly used in a program, and our neural network jointly performs localization where it locates the bug, as well as repair where it repairs that bug. You can read more about it in our paper. Next, I'll talk about how we utilize software engineering and formal methods to aid machine learning. So in this technique, we basically built a model that mimics a deep reinforcement learning policy that is a neural network, and then can be translated to SMT logic and be verified. And it's more performant, it has better representational power than decision tree. Our model is called MOET, Mixture of Expert Trees. Also, you can read more about it in our paper. In future work, I plan to explore these connections of different models of computation, molecular programming, classical programming, and machine learning. And my contributions related to this talk are: I designed the first imperative molecular programming language, as far as I know. I designed a technique that systematically explores space of CRNs, discovering extremely compact CRN which computes the ReLU function, and achieving best UN paper award at DNA conference. I discovered a tight connection between neural networks and chemical reaction networks using rate-independent scheme. I was involved with 3 more people in DNA wet lab experiments, implementing and experimentally verifying our neural network to CRN scheme. And I argued the importance of examining other forms of computation, such as analog, and building a holistic view unifying distinct kinds of computation. So as far as we know, there's 3 kinds of computation happening on Earth. 1, computation within our computers. 2, computation within our brains, within neural networks of our brains. And 3, computation happening within every cell of every living organism on Earth within complex gene regulatory networks. I explored connections between these different models of computation, and I believe by building a unified view on computation, we'll get fruitful results. So I'm glad you are here, because by being here you expressed an interest into emerging field of unconventional computing, and by doing so, I think that we all started contributing to advancing the field and building more exciting applications to public.